If you clicked on this video, you're probably interested in innovation in product design. Instead of just like looking at the latest innovative products, wouldn't it be more interesting to talk about how innovation actually happens? Now, there are different ways innovation can happen. However, what I've noticed in my own practice as an industrial designer is that there is one way of thinking that is responsible for innovation, invention, and just figuring out all the details that need to be figured out in the course of designing a product. And, you know, like Charles Eames says, the details are not just the details. The details make the design. The last example is from a product that I worked on, which is this product, which is the Muse. It's a brainwave sensing headband. And I'm going to show you how we use this way of thinking to help at the beginning of this project. So be sure to stick around for that. This one way of thinking is responsible for how a Chicago slaughterhouse inspired a huge innovation in manufacturing history and really changed how all products were manufactured. It's responsible for how a bicycle grip inspired a kitchen utensil, and also how sparks rising from a fire inspired a new form of air travel. It is also responsible for countless scientific discoveries. It's rated among scientists to be one of the most important mental skills to possess. So this way of thinking is called analogical thinking. And analogical thinking is when we take information from one domain and use it to help solve a problem in another domain. And if you're wondering what an analogy is, I'm going to use the definition out of this book, which is called Shortcut by John Pollock. It's a great book if you want to read more on the topic. And the way that his definition, an analogy is simply a comparison that asserts a parallel, either explicit or implicit, between two distinct things based on the perception of a shared property or relation. It's between a children's arm floaty and the Pulp stool. Now, if you're not familiar with the Pulp stool, it has won some awards. It's quite unique looking, and that unique appearance is a result of their innovative forming method that I think they created this new way of forming sheet metal. The analogy here is in how these two objects are formed. First of all, if we look at the similarities, so the arm floaty starts out flat. It's a PVC material. It is heat sealed around its edges. The Pulp stool starts out flat as super thin sheets of steel that are welded around the edges. And in both cases, there's the potential for an air pocket in both. And how they are formed is through air. You know, when you blow into the arm floaty, that's what, you know, creates the form. In a similar way, the Pulp stool, it's formed by inflating the pocket inside these two metal sheets under really high pressure. And that is the thing that gives it 3D form. It may not be the most comfortable form. Maybe you want to put a pillow underneath there. But the analogy here is between how to form sheet material with air. Now, I wanted to read you this quote from John Pollock, where he points out that it's nearly impossible to innovate without using analogical thinking. Although researchers, inventors, and developers often don't realize in hindsight the role that metaphor played in helping them achieve their breakthrough ideas. In order to create something new, you must model your work on something old. So let's talk about the OXO Vegetable Peeler. This is quite a famous design in terms of innovation in product design. So the designer set out to design a grip for people who have challenges gripping things, such as people with arthritis.
So the designers identified and actually used an innovation in crayons to help guide their thinking in how to make a better, easier grip. And this innovation was the jumbo crayon. And if you are not familiar, the jumbo crayon is really just a crayon with a larger diameter. And the purpose of this larger diameter is to make it easier for small hands to grip the crayon. And they made the analogy that it's the same thing for people with arthritis. They also need something with a larger dimension. Now, the next step in the process was they found that, having a squishy area between the thumb and the index finger also made it easier to grip. And they found a way to achieve this in the part design, but it was all kind of inside the part, like you couldn't see it from the outside. And their client pushed them to make that detail visible so that at retail people could see and imagine what would happen when they picked up this grip and put it in their hands, and they could see how that squishiness or something was happening in that area.
So the story goes, the designers stuck a bicycle grip onto the metal cutting part of a vegetable peeler and discovered that it actually felt really comfortable in the hand. I think it's a functional analogy in terms of how the grip functions in a person's hand, how it kind of performs. But if we look at the similarities, what these things share is that they are things that you put in hands, and in both instances, this is a grip. One great example from nature is Burrs and Velcro. So I think it's kind of easy to just skim over these stories and be like, oh yeah, that happened. What's next? But what I'd like to do in this video is sort of unpack each story and look at images, look at the pictures, and really try and figure out what actually happened in each of these situations. What was the analogy and what can we learn from it? The man who invented Velcro one day went out with his dog on a walk, came home, and both him and his dog were covered in burrs. And he noticed that they are very difficult to get off of you. I've had this happen to me. When I was a kid, I fell into a burr bush and there were burrs all in my hair, and to the point where I had long hair, and then that day they cut off all my hair because they couldn't get the burrs out of my hair. Burrs are very, very good at sticking to things, and that is the quality that he noticed. And what he did is he then put the burr under a microscope and found that in the burr actually has a little hook on the end of the kind of spike. The analogy here is a functional analogy, and it's kind of saying that if we could recreate the form of a burr, which is a spike with a hook on it, if we could recreate that in a manufacturable form, we could also recreate that functionality, which is, the ability to stick to something really, really well. If you are someone who is interested in biomimicry, biomimicry hinges on analogical thinking. Biomimicry doesn't work without making an analogy, without looking at something in nature and using it to solve a problem in a design. Designers don't just draw pretty pictures, they solve problems. Well, analogical thinking is one of the key ways that designers, I think, naturally, intuitively solve these problems. Let's talk about Ford's moving assembly line. Now, if you're not familiar with the moving assembly line, it was a huge innovation in manufacturing history in terms of how it changed the price of the car, and all of a sudden the car became so much more accessible to the average person. But I'll get into that in a little bit. As the story goes, it was not actually Ford who discovered this. It was Bill Clan, who was a Ford employee. He took a trip to a Chicago slaughterhouse. He saw how the slaughterhouse was set up to dismantle a carcass. And how this worked was the carcass would be hung up on a hook, and then it would move from station to station. And at each station, one person would, do their thing, take off whatever part they were responsible for, and then the carcass would move on to the next person who would remove their part. So the carcass was moving through the moving, assembly line. It was between taking apart a carcass was fundamentally similar to building something. It's really just in the opposite direction. He had the vision to see that if Ford could adopt the moving assembly line, they could increase productivity and reduce costs. And after seeing the success at Ford, it took little time for every other industry to imitate the moving assembly line. So it really was a huge game changer. And if you're curious about the numbers, so the moving assembly line allowed the Model T price to drop from $575 to $280. Wow, that's a big drop. That you're drawing insights from one field and applying it to another. The act of forming an analogy is a mental leap, okay? And it requires us to see one thing as another. The hot air balloon is an interesting story because not only was the inventor trying to solve a problem, but the thing that he was looking at while he was trying to solve that problem was the thing that gave him the idea. So the story goes that Montgolfier, who invented the hot air balloon, was staring into the fire. He was thinking about a battle that had just happened where his side had just lost a fort. And what we know about forts is that they're very hard to penetrate from the ground, right? Everyone inside the fort has a distinct advantage over everyone else. So he was thinking about this loss and staring into the fire, and there's this crackling, okay? And if you've ever stared into a fire, you know that when it crackles, usually there's like little sparks that go up. And he sees these sparks and he has an idea. He thinks, well, what if we could penetrate this fort by air? And what he does is he constructs what could be called a prototype. He gets a piece of fabric, constructs a prototype, and lights a piece of paper underneath it, and lo and behold, it rises. The hot air rising from the fire, right? The spark is rising because it's in hot air. If you could trap that hot air in what's now known as a balloon or in fabric, then you can lift something. The topic of the video was form follows function, and just looked at one example, which was innovation in nail polish brushes. So if you are not familiar with nail polish brushes, in the past all of them have tended to be round, and if you have ever tried to put on nail polish, it's kind of challenging. And this nail polish brush was a flat brush. But the analogy that I made in that video was between nail polish brushes, this specific brush, and fine art brushes. If you look at brushes in fine art, each type of brush has a different use. It has certain benefits. It wants to behave in certain ways, right? Like round brush, it's much easier to do, let's say, calligraphy with, because it's kind of like, it swirls around and it just has a different characteristic, it has different behavior. Whereas, you know, a flat brush is a lot more stable. It puts down more paint on a page faster. So it has different characteristics. And using that analogy between nail polish brushes, which are, you know, consumer product, and fine art brushes, which is also a consumer product, but in a different domain, okay, fine art, beauty. So these are two things in different domains. And, you know, if you were someone working in the nail polish industry, that could have been one avenue you could have explored, was okay, how do we make a better brush? Well, if it's about making a better brush, you could look into different industries, different other ways that brushes are used in the world, and get ideas about the characteristics of different brushes, and then bring that information back into the nail polish industry and into your, into your design. So I wanted to give you an example of how analogies are used in the details of a product, because while these can seem, the details in a product seem much less like sexy than like an invention where you get a patent, the majority of what you do as an industrial designer or product designer is figure out how to solve all these small problems in the course of designing a product, okay? And all of these small details are what make the design, like Charles Eames says, right? They are the design, yeah? And in this example, this is an example of pulp storage, which is a paper pulp product. And I have one, just a minute. Okay, this is the product. It's a paper pulp storage container, okay? Now, I have a video just on this product, if you're interested, and I'll put a link somewhere, and it's kind of a product analysis of like, of the industrial design of this product. So you can, if you're interested, you can go watch that. But this product is a container. It's a storage container for like pens, or it's kind of like could be a pencil case, or could really store anything. So it has a main container, a lid. Now, what you'll notice is there's some friction that keeps the lid in, but not a lot. So in the course of designing this product, the designers would have seen this or tested it out and be like, okay, how are we going to keep the lid on the container? They would have brainstormed, what are all the possible ways we could keep the lid on the container? And if they were like me, I would like go out and look at all the things in the world that hold a lid onto something or hold something shut, okay? So I would start to brainstorm, what are all those things? And just make a list. And then go and look at those things online, maybe, or in person if you want. And one thing that is very similar to the idea that they came up with, which is the way to hold this on, which is just an elastic, okay, to hold the lid on, it works, is if they looked at a Moleskine book. This is not actually a Moleskine, it's another brand, but Moleskine has the same thing as does this book, right? It's an elastic, and it keeps the book, the pages closed, right? The whole book closed. And, while these are two different products, they actually happen to be made of the same material. They're both made out of paper, but the elastic performs the similar functions, right? Keep this closed, yeah? So I realize that this seems may seem very simple and maybe like, yeah, duh, but when you're designing a product, you don't know what that product looks like before you design it. So that process, you are moving in a direction where you don't really know the future, the end product yet. You're still figuring it out as you go. So anytime you can look out into the world and see something that's finished and be like, yeah, I want to work, I want my product, I want my design, I want my design to work like this, then all of a sudden it's like, oh yeah, of course. And you've got an idea and you can see how it works, and you can make a very good guess that it will work for your design. Now, what I'll also say with the pulp storage is, in making this kind of analogy, and I don't know if the designers of this product saw a moleskin and they're like, oh, let's use this. But I can tell you that that is how my mind works, and that's how I find ideas for my design work. And I want to let you know that one of the huge benefits of using analogies in something real that you find that's already manufactured, okay, is that this is what I would call like a functional analogy, in that if they had found the idea here in the book, in the elastic for the book, it's in how it functioned. But the bonus of finding ideas in the real world is that they come with a material, and this has been manufactured. So if you're someone who is not familiar with manufacturing, not familiar with material properties, it's like those things are like built into this idea, because you don't get this function without this material, right? So it's an amazing way, especially if you're a young designer, using analogies, because you have the material built in to your kind of source of that idea. Yeah, so there's a huge benefit. This is the final example. Let's talk about the Muse brainwave sensing headband and how we used an analogy at the beginning of the project to help guide some of our thinking. The thing with this product, there really wasn't anything like it in the world. There was no like predecessor to this product. Perform in certain ways. These are the things that the design has to do, okay? So we knew what the design had to do, but we didn't know what that looked like. At the beginning of a project, you continue to go over all of the things that are required. They're the requirements of how your design needs to perform. But what that looks like could take many different forms. When we're talking about the requirements of that project, one thing is that, you know, the EEG sensors have to have a certain amount of, they need to touch the skin, but they have to have a certain amount of force on the skin to conduct a signal. Like, they can't be loose, you know, floppy on the skin. They need to be on the skin, so you have to have some amount of force to get a signal. But when you start to look at people's forehead shapes, it's like there's so much variation. You know, some people have the forehead that, like, you know, juts out and is like full semicircle forehead. Some people have like totally flat foreheads. And I totally encourage you, if you're in public right now, just take a minute and like look around to all these people, the people that are around you, and take a look at their foreheads, because I tell you, everyone is different, and it makes for very, very challenging when you're trying to fit something to foreheads. On the headband, there was actually a piece of elastic here. So this part was malleable, soft. It would adapt to different head forms. But then it had a harder aspect that provided a structure on the outside. That idea that we found in the headphone, that, you know, outer structure and that but inner kind of conformable aspect, is also repeated in the earpieces, which, if you can see that, this part is the outer structure, and then there's an inner compressive, soft, moldable, not moldable, but malleable aspect that is comfortable behind ears. If we look at some of the similarities, there's quite a number of them. I mean, both things, they are meant, they're designed to be on heads. Both things have and relate to, in some way, to ears, okay? So what these two things share is you know, having this outer part, which is like structure. Well, it joins two ear parts. It also has like spring steel, similar to headphones, which just means like the spring steel will always want to come back to its original form. So the spring steel kind of like holds it on the head, but also you can lift it off, but then it wants to come back. So we have structure here. We have this inner part, which is, you know, is able to adapt to different people's foreheads, similar to, you know, the headphones. Now it's a different form and a different material, but it still has that same idea of this needs to be compressive, this needs to be comfortable, and as you can see, the form is and material allow that to happen. So, you know, while it's not like a direct line from one thing to the other, it has the qualities that we were looking for, but there was another way to achieve and get those qualities in the design. The headphones did a lot of the things that we wanted our design to do, and the reason why is because of their form and their material. It helped us to identify those material qualities and things that we wanted in the design in order for it to function. So I hope you guys enjoyed this video. It might have been a little bit of a different kind of video, and always happy to hear feedback on what you think. And yeah, have a great day. See ya.